Thanks, Lorenzo, for the invitation. And I'd like to thank the organizers for putting together this wonderful conference and also for inviting me to give this talk. So what I'm going to talk about is an overview of work on the topic that I've put up there. So this is, it was published in a number of papers in joint work with collaborators, so John Gove, Matt James, and also Josh Coombs. So this is an overview of what I want to talk about today. So I'm going to start with quantum I/O systems and what the problem is. So basically quantum input-output systems and in non-Gaussian states. And then I'm going to digress a little bit and talk about classical estimation problems and continuous time filtering. And that's because because one of the techniques, the next part of my talk is I'm going to talk about different methods you can do for describing dynamics of systems coupled to non-Gaussian states. And one of these is motivated by this connection to classical estimation and filtering. And then I will also give some numerical example. And finally, I will conclude my talk with some conclusions. OK, so this is the kind of systems that I'm going to be talking about. So we have a Markovian system that's coupled to an input field with an annihilation operator B in. So this comes in, interacts with the Markovian system, and then goes out, so you get an output field. So this incoming field, they have this commutation relation. So there should be a dagger there. I forgot the dagger, but anyway, they satisfy this singular commutation relation. So this object, it's a traveling field. This is a complicated object because it can contain many modes, and it can contain many photons. So it's not an easy object to analyze. But anyway, so these kind of systems, of course, are of interest if you think about modular approaches to quantum information processing. So you might have different processes that transfer information to one another, and so you get these traveling fields to transmit information from system A to B, and so on. OK, so quantum input-output theory, of course, it's a well-developed topic. So it originated in the work of Gardiner and Collette in 1985. So, but the standard setting for quantum input-output theory is really this Gaussian state, so coherent state, squeezed vacuum, and so on. But in recent years, you know, as people start to develop ways to do quantum information processing, there's been interest in also fields which are non-Gaussian. So I'll give you some examples of interest. So that would be like the one photon state with a temporal mode function psi. And you can use this, for example, as a flying qubit. You could put a superposition of a vacuum state together with the one photon state that you encoded in this traveling field. And then you can also have multi-mode, multiphoton states where you have multiple modes. So these multiple modes have different temporal mode functions, and they can have different numbers of photons. And you can also talk about flying cat states. So you have a linear superposition of coherent states Fk, where each of these Fk's is just a square integrable function. So all of these four states I'm going to talk about can be treated with one, if not both, of the techniques that I'm going to explain later in the talk. But for example, because of the time restriction, I will probably just give examples relating to just the single photon state. OK, so the dynamics that I'm talking about are of interest. So there's really two types that you can think about. So the first one is unconditioned dynamics. So these are what's called the quantum master equations. So this is just the reduced dynamics of the system alone after you trace out the field. Or you can think about if you have measurements, you're just ignoring the measurement, and then you're averaging over the measurements. The other one is the conditioned dynamics. So this is, in some communities, it's called the quantum filtering equation, while in other communities, it's called the stochastic master equations. So this is the dynamics. So you get, when you measure the quantum system continuously, then you get stochastic dynamics, and that's what, and we want to be able to describe the dynamics of the system condition on those measurement results that we see in, say, in an experiment. OK, of course, the continuous time monitoring is a basis for doing measurement-based feedback control. So you can do some measurements. So your input field comes in, interacts with your Markov system, and then comes out with producing an output field. And here you can put a detector to do some measurements, and that will give you an output yt, which can be processed by a classical controller to give you input function. So you can, based on the measurement record that you get, you can produce an output function which you can send back to the system to control it. So this, so of course the pioneers in this area include Belavkin, Wiseman, and Milburn. And so in relation to these non-classical states that I mentioned earlier, non-Gaussian states that I mentioned earlier, so you can see, for example, recently continuous monitoring using homodynamic detection of the single photon state field has been demonstrated. So this was in this paper from Akira Furusawa's group. But I suspect that it can also be done in other platforms as well. Okay, and of course, besides quantum feedback control, the other important application of this stochastic master equation is for Monte Carlo simulation. So you use that to numerically solve the master equation. And so this goes back to some work in the 90s by 3 independent groups, or maybe more, who proposed this method to numerically solve the master equation. Okay, so now I'm going to digress a bit. So I'm going to leave the quantum setting, and I'll come back to it. But I'd like to go now to a classical setting of filtering theory. So I'm just going to explain what this is all about. So filtering theory really goes back to the work of Norbert Wiener in the 40s, where he developed this theory called Wiener filtering theory. So this was the first type of work in this direction. So the setting that was considered there is that you have 2 stationary jointly Gaussian processes. You have xt and yt. Okay, so you're only interested in this process xt, but you can't observe it directly. You can only observe it through this yt. So but because so we assume they're correlated, so you want to learn something about xt from observing yt. Now, so the problem data in the original setup of this problem by Wiener is that you have information about the autocovariance of yt and also the cross-covariance of xt and yt. So you need this cross-covariance, because if they're not correlated, then you don't learn anything about xt from yt. Okay? So the formulation of this problem is an optimal optimization problem. So what you do is, in the original formulation by Wiener, he poses as a mean square optimal optimization problem, where xt is the signal you're interested in. So you assume that you're going to take your estimator of xt, a filtered version of yt. So this ht is the impulse function of a filter. So you pass ys through that filter, and you have to find what this filter is that minimizes this mean square error function. So if you can solve this problem, and which Wiener actually did, then you can find this optimal estimate of xt, which I denote by x hat optimal, as just putting this observation yt into your filter. So you pass it to the filter, and you get your optimal estimate of x. Okay, so that was Wiener's work, and later on, people start to think of this problem in a different way. So rather than assuming that you know the correlation and autocorrelation function for your signals, you assume that you have a dynamic model for how they are so how they're related through this dynamic model. So this goes back to work by Stratonovich and Kalman, and for this kind of framework, you don't need the stationarity anymore. So, for example, the easiest or the simplest model is something which is a linear model like this. So x evolves linearly. So here you have the noises wt and vt. So they're just Wiener processes. And then so here you have a dynamic model for the evolution of xt and yt, and the yt is related to ht through this measurement equation or output equation. Okay. So the standard assumption in the setting is x0 is Gaussian, independent of the 2 noises that drive the system. Okay. Right. So in this setting, again, you can pose the same problem that Wiener did of minimizing. So what you want to do is you have the xt. You want to find some function of your observation, so you minimize this quadratic cost in the error between estimating xt with a function of yt. Okay. Now the solution to this is it's really that your optimal estimate xt should be the conditional expectation of your xt, conditioned on the observation that you have over the time interval 0 up to time t. Okay. So it's the same problem, but now really what we're doing is computing this conditional expectation of x, okay? So what happens in this setting is we have a dynamic system like this that's evolving over time. And then when you compute this conditional expectation, the nice thing is that you actually get also a dynamic system that produces the estimate for you, okay? So this is what I call computed recursively. So in bracket, in between quotes, because where you have a continuous dynamics, what I mean by recursive here is that the optimal estimate itself is you can evolve as a dynamic system, okay? So this is a stochastic differential equation. So you have, so this part here, it turns out it's going to be this term here. It's going to be just another Wiener process. And this dynamic system that produces the estimate for you, that's called the Kalman-Bucy filter, okay? So basically the Kalman-Bucy filter is again a linear dynamical system, yeah, that's driven by your measurements. And so it also has this gain, which you can compute offline because it doesn't depend on the state or any other parameter. I mean, it's something you can compute beforehand, and you don't have to do it online while you run this filter. So this is the linear case. You can extend it also to more general dynamic systems that look like this. So you have, again, you have an evolution of xt that's driven by white noise. You can have nonlinear functions for the b and sigma. And then you have an output y, which can also be related nonlinearly to your state through this noisy observation model, okay? So in this nonlinear case, what you aim for is to compute the conditional expectation of a function of xt for a generally sufficiently large classes of functions f. And so often what we want to do is sometimes it's convenient to try to, rather than propagating the conditional expectations, you want to propagate the density operators associated with your process x. So you can do that. So if it exists, then you can also, from the equations for the dynamics of your conditional expectation, you can also get the dynamics for your probability distribution. So I'm gonna just stop here. There's more that I can say about this because, for example, filtering is used also for feedback control in the classical setting. So you can use the output of filter to drive a controller, but because of the time limitation, I won't get into that. So I'm just going to now go back to the classical setting, the quantum setting that we started with. Okay, so so we had this input and output process before. So now these are extremely singular objects that satisfy that delta correlation, delta commutation relation that we saw earlier. So now I'm going to introduce this integrated processes bt, v hat of t, and this lambda t. So they're different processes, but now they're integrated processes. So bt is just an integral of your annihilation process. bt dagger is an integration of your creation process, and lambda 2 is just it's an integration of the number operator for your field. So these are singular. I mean, they're still very singular objects. They're the equivalent of like complex Brownian motion, and so they satisfy also a quantum version of the Ito product rule. So if we take our state of the field to be in vacuum, then the corresponding Ito rule is going to look like this. Okay, so you have these products between the forward differentials of these processes that I just defined, and you have these non-trivial products, but all the other products are equal to 0. Okay, so now we want to describe the unitary that couples the field to the system. So here is what's called a quantum stochastic differential equation. So UT is a unitary propagator that connects that governs the evolution of the joint evolution of the system and the fields. Okay, so it looks like this. So, the H here is the Hamiltonian of the system. L is an operator that couples the system to the field, and here is and S is a unitary operator on the system. Okay, so to give you a concrete example, so let's consider an optical cavity, a single mode optical cavity. So for the cavity itself, you would have the internal Hamiltonian, which is just omega 0, the resonance frequency of the cavity, and then you have A dagger A. So that's a Hamiltonian. Usually this cavity, you have a coupling to the field through its annihilation operator. So you have in this case, you would have the L is equal to square root gamma times A, where gamma is the decay rate of the cavity. And for the S, you would have something which this has to be unitary. So you can just take, for example, you can take this to be just a a complex number which has magnitude 1. So that will represent, for example, a phase shift in the input to the cavity. Okay? So this gives you, so the solution of this equation is going to be something which is unitary, and so it describes the evolution of the system. Okay? So basically this idea was originated in the work of Gardner and Collette, as I mentioned earlier, but the stochastic calculus that described this was already developed by Hudson Prasarati before the quantum input-output theory was developed. And so so there's this very nice paper that was recently, appeared recently by Coombs, Joe Kirchhoff, and Mohan Sarobar that explains this and emphasizes the physics of these equations. So I think that's a very good place if you want to know more about these equations. Okay, so then we can go to the Heisenberg picture. So if I take any system operator x, then we can evolve this, you can take the evolution. So this JTX is just this conjugation by UT dagger in the front and UT at the back. So that gives you the Heisenberg evolution of XT. And you can apply the Ito rules, and you can get that. If you write this out and you compute the derivative of XT, or the differential of XT rather, then you get an equation that looks like this. So you can also evolve the output field, the input field for your system. So again, you can sandwich that between UT dagger and UT, and you get the output field for BT, and you get also the output field for the process gamma T. Okay, so if you write down the evolution, then you could get something that looks like this. Okay, so now we can do some measurements on the field that we have, and there are many. I mean, there are potentially different observables that you can measure. So let's suppose that we're going to just consider two different kinds of measurement you can. So you can measure the real quadrature or the in-phase quadrature of your field, which is BT plus BT dagger, or you can measure just count photons. So then the observable you're looking at is just this process lambda T. And so then if you, in the Heisenberg picture, what you get is that the evolution of this, so we're going to use this notation YT to denote the output of our system. So that we will be looking at two possible outputs. So this is, if you measure BT plus BT dagger, then you get homodyne detection. And if you measure UT dagger gamma T UT, then that's really a photon counting measurement. Okay, so all right, just a few properties of these systems equations that's useful. And the first is this property called adaptedness. So really, what's happening? So forget about what I've written up there. What it really means is that the field, it spreads over time, right? And the Fock space of the field, Hilbert space of the field is just the boson-Fock space, and so you have a temporal decomposition of this Fock space into sections of time, right? So adaptedness means that if at time t, when you act this on the system, these operators ut or xt or yt, they only act on the portion of the system plus the field up to time t. Okay, it doesn't do anything to the part of the field that hasn't interacted with the system. And the other two important properties of these models is that you have this commutation relation xt and ys. So if I take xt evolution of my system operator x, and I take ys, which is my evolution of my system, then these two will commute for all s less than t. So the xt at time t commutes with y for all times s less than or equal to t, and also we have that yt commutes with ys for all st greater than or equal to 0. Okay, so this is an important point. So these two properties are crucial. Okay, so what do they tell us? So basically, it tells us that if I form this family of observables, so xt and ys for all s between 0 or up to t. Okay, what that's telling us is that all of these observables, they are commuting, and so they're simultaneously diagonalizable. Okay. A consequence of this simultaneous diagonalizability is that you can map all these observables into a random variable, and then these random variables will have a joint classical probability distribution. Okay, in general, if you have two incompatible observables, then you can't have this joint classical probability. Okay, so what that means is that we can do what I talked about earlier. You can compute you can do this conditional expectation on these observables. So what I mean by that is that if you have, so since xt commutes with your observation up to time t, this notion of conditional expectation again exists in this setting because of these two properties that we have. So here I've written this notation xtc, which means the conditional expectation of xt given your observation record from 0 to t. And so when you compute this, you get an equation, which is again, as in the classical case, you get a stochastic differential equation for the evolution of this conditioned quantity. And this is what's known as the quantum filtering equation. Okay? Now we can express this conditional probability as a trace of rho hat times x. So x is the original observable. And rho hat of t is just it's a stochastic density operator. And so from the equation for this object here, you can get an equation for rho hat of t. And this is what's known as a stochastic master equation. Okay, so something that quantum filtering theory does tell you is that there is an optimality in this stochastic master equation or the quantum filtering equation. So what the optimality that we saw earlier in the classical setting also holds here. So these conditional expectations, they minimize this kind of cost function where xt is the observable you're trying to estimate, and f of yt is some function of your observation from time 0 up to time t. So we still have this optimality property that we had also in the classical case. Okay, so now I'm going to go to the core of this talk, which is really how, describing these techniques for describing the evolution of systems that are interacting with non-Gaussian states. So let's go to the single photon state. So basically, you have this temporal mode function, which integrates from 0 to infinity. So it's normalized, it integrates to 1. And then we can define what's sometimes called broadband mode operators. So b of psi, so psi is your temporal mode function. And so b of psi should also, there shouldn't be this here. So the operator itself is just this, okay? But if you act it on the vacuum, then you get the one photon state. So a property of these broadband mode operators is that they satisfy this commutation relation, and you can recognize this as a commutation relation between the annihilation and creation operators for a single an harmonic oscillator, right? So that means that you can, so they have the same commutation relation. You can define things like this. So you can define the n photon state of the field, right? So you have that you can apply the annihilation operator n times onto the vacuum, and you will pick up n photon state of the field with this temporal mode function psi. Okay, so that's something that you can have in these fields. Right, so now I'm gonna go into the first approach that we developed for dealing describing this evolution. So let's take a one photon state, one psi. So both techniques I mentioned earlier involve lifting the problem into a larger Hilbert space. So what we do here is that we're gonna couple the system to an ancilla. So you put into an enlarged Hilbert space, and we set up the system to be initially entangled. So what's really entangled is not really the system, but rather we entangle the ancilla with our fields. Okay, so we assume we take an entangled initial state that looks like this, where this is normalized, of course, and we have alpha 0 and alpha 1 not equal to 0. Okay, so but there's nothing else. There's no other interaction between the ancilla and the field other than this initial entanglement. Okay, and the other thing to note is that this embedding, because of this, we still have the one photon state here, right? The embedding itself is going to be a Markovian embedding. Okay, so the trick to doing this is that, so we're now on the extended Hilbert space. So let me take an operator A on the ancilla, and then I can compute the expectation of any tensor product of an operator on the ancilla with the one on the system, which is X. Okay. So I can express this in this way. So I can express them in this linear combination of these other quantities, which I've given the superscript jk. And this jk is going to be related to so this expectation on the extended Hilbert space is going to be related to this quantity mu t of jk through this relationship right here. Okay? So this is easy to compute. What's a bit more surprising is that you can do a similar thing at the conditioning level. When you condition these equations, when you condition xt on the observation on the extended Hilbert space, you get something that looks like that as well. So you can relate the conditional, you can introduce this condition quantities jk with index j running from 0 to 1. Okay, so there will be 4 quantities when you're looking at the single photon state. But really, the only physical one is the one with the index 1, 1. Okay, so you can relate these quantities into conditional quantities on the extended Hilbert space. Okay, but the only one that's of interest to us and that's physical is just the 1, 1 case. Okay, what's particularly, I guess, surprising is that even though you've embedded this system into a bigger system, which is still non-Markovian, you can actually compute these conditional quantities. Okay, so because of this relationship, once you have the conditional quantities on the embedded space, you can compute each one of these, and you compute the one with JK is 1, 1, so that gives you the conditioning that you want, that you're looking for. Okay, and then once you have this quantity 1, 1, you can write that as a trace of a random density operator 1, 1 times x, and this will give you the equation for the evolution, the stochastic evolution of your density operator when the system is coupled to a single photon state. So this really uses ideas from classical estimations. And in classical estimations, there are different ways that you can approaches that you can use to compute the conditional expectations. And one technique is called the reference probability approach. And the quantum version of this was developed by Belton and Van Handel, and that's been used here to compute this conditional expectation on the extended Hilbert space. Okay. So if you do work that out, so you get this is a master equation for your system. You can see the dependence. So now it's a bit different from the Gaussian case. The Gaussian case, you don't have this coupled equation. You only have a single equation. But here you have coupled equation between the 1, 1, 1, 0, 0, 1. So we have the relationship that these two are conjugate to each other. And then you have this initial state for your system when you propagate the master equation. So you can see that the temporal mode function appears in this equation. So actually, this equation was already obtained by Gary and colleagues in this paper from 1998. So here we've extended that to include this scattering matrices S in these equations. But the conditional equation really was done for the first time in this paper. Okay, so that is the master equation. And if you compute, do the computation for the conditioning, you get something like this for the stochastic master equation. So here you have a system, a stochastic system that's driven by this quantity dWt, and dWt is just a difference between your measurement record, the measurement that you make, and this conditional quantity. So this gives you the just to show you what the stochastic master equation looks like when you apply these techniques. So there's also this is under homodyne detection. You can also do photon counting, but I'll skip that and move on to the next method I want to talk about. So the other approach is to use a cascading approach for quantum systems. So this originates, of course, in the work of Gardner and Carmichael, and I think there are other people who also discovered this principle independently. But it's also a principle that's known in the classical setting as well, because in the classical setting, you can produce colored noise by driving white noise through a filter, right? So it's a similar principle, okay? So really in the quantum setting, what we're doing is that we have to set up a source model, okay? So this source model, for example, here I'm taking it takes in vacuum, and it produces the non-Gaussian state that you're looking for, okay? And that non-Gaussian state you pass through the system, and then so you can then study this whole cascaded system, because you're back to the familiar situation where you have a driving by a Gaussian state, which in this case is a vacuum. Okay, so I'm just gonna. So we wrote a couple of papers on this approach. I'm just gonna take the most general one that we have. So we take a non-Gaussian state of the field that's a continuous matrix product state that looks like this. So we're assuming that you can generate this state by passing vacuum through a Markovian system, and then as you let time go to infinity, so the system gets entangled, but eventually asymptotically the system of the field becomes disentangled. Okay, so you can then trace out the ancilla, and so then you get a pure state of the field. Okay, so as I will show later, this kind of continuous matrix product state includes time-ordered multiphoton states and Fock states of the field as well. Okay, so just to be concrete, I'll give you an example of a generator for this kind of system. So here we take an n+1 level system with levels L0, L1 up to Ln, okay? So we're gonna take the Hamiltonian equal to 0, and then we're gonna define, so here, let me go back just a bit. So we have the Hamiltonian for your source model, and then you have this operator RT, which couples the source model to the vacuum. And then here we have the initial state for your source model. Okay, so if we do, so I take RT to be of this form. So this RT connects LK with the LK minus 1, so it destroys LK and creates LK minus 1, this level, and then it's modulated by something which is time dependent. Okay, so it becomes a bit complicated. This coupling lambda KT looks like that, and this is computed recursively. So you compute this lambda K and WK for K is 1, 2 until n, and then you start from the Wn plus 1. So this Wn plus 1 equal to 1 allows us to compute all the lower index for WK. Okay, so if you initialize the source model in the state Ln, what will happen is that it will produce this kind of state. But this is what we call a time-ordered multiphoton state, because there's time ordering going on in this state. But if you have all the mode functions are the same, so psi 1, psi 2, they're all the same, then you get the n-photon Fock states for your field. Okay, so there is an open problem which I'll discuss later, which you cannot produce by this method. Okay, so then once you have the source model, you're back to familiar territory, and so then it becomes quite easy to recover the unconditional and conditional dynamics of your original system from the embedded one. So all you're doing is just tracing out the ancilla. Again, the unconditional dynamics already appeared in this paper, but we use these techniques to get a stochastic master equation with different approach. I mean, same approach, but in different levels of generality. Okay, so just to give you an example of what happens when you simulate this. So here we're assuming just it's a qubit with 0 internal Hamiltonian. We take the coupling to the field to be just the lowering operator for the qubit, and then we take the S to be identity. And then we allow this system to interact with a single photon field with a mode function that looks like this. So it's a Gaussian with a center at TC. So from this picture here, the center is around 3, okay? And we take this parameter gamma to be 1.46. So this is a result of simulation that was done in this paper. So you can see here, this is, so here is the square of your temporal mode. And here, so here is the trajectories of the system for individual measurement records that you have. And you see this red line, that is the actual calculation of the master equation that we get from the equation that I showed you earlier. And the green ones are the averaging over these trajectories that we have. Okay, so we only have like, in this simulation there was 100 trajectories, so it's still a bit noisy, but you can see it follows the pattern of your master equation. Okay, right, so, all right, so I'm almost at the end, so I hope I'm on time. Yes, okay, so I may have rushed it a little bit, okay, so anyway, so an important extension of the single photon case that we did is to the multimode multiphoton state. So that was done by Song, Zhang, and Zi. So there's been some analysis of oscillator-based source model by Gov and Zhang, which was published in 2015. And more recently, there have been alternative derivations for these equations, so including this work by Barigiola and Coombs in 2017. So they basically got a different derivation of this what we had for this single multiple photon state, this one here, by using quantum measurement theory rather than the approach that we've taken here. And then there's also this work recently by Darbowska and her colleagues. So what she did there is, what they did is to derive these equations from studying the continuous time limit of discrete time repeated interaction models. So they show that if you take a repeated interaction model and then you take the continuum limit, then you recover the equations that we get. So there are other alternative derivations that have appeared since we published these results. And also there's this work that combines more than one measurement on the single photon field. So this work by Dong, Zhang, and Amini, so Go Feng and Nina are both here. So what they did is they put a single photon through a beam splitter, and one output of the beam splitter they do homodynamic detection. On the other output they do photon counting, and then they derive the conditional dynamics under this kind of measurements. Okay, so just to conclude, so what we've done is for these systems we've developed two different techniques, non-Markovian embedding and Markovian embedding. So there's some pros and cons about in using this technique. So for the Markovian embedding is that you don't rely on a source model. Okay, so that's one of the pros of using that approach. Well, I don't know if this is a con, but it's really, I guess it depends on how you look at things. But some might find that it's not appealing because there's no physical interpretation of what's being done, right? It's purely a mathematical trick that you do to get the condition, the equation for the conditioning, okay? Now, for the Markovian embedding, of course, the pro is that it's clear what's happening. So you have a source model that generates the state you're looking at, and you're driving your system with that source model. But what's difficult about this is that you have to get a source model first, right, before you can do anything. And that's not easy because, for example, this is still an open problem. The problem has already been solved, right, for this multiphoton state that was in the work of Song, Zhang, and Zi. But still, it would be nice if you can actually have a source model that generates this multiphoton, multimode multiphoton state that takes this form. And this is currently still missing. Okay, so that brings me to the end of my talk, and thank you very much.
We have quite some time for questions. I see one coming here, Daniel.
Thank you. So if I understood correctly, the unconditional dynamics, so the Lindbladian in your case, is time-dependent Lindbladian then for the non-Markovian embedding.
You mean this equation?
Yeah. Yeah. So that's basically, you can still write a differential equation for the reduced dynamics, but the Lindbladian generator is now time-dependent explicitly. So
we don't have a Lindbladian generator. It does make an appearance, but what you have here is a coupled set of 4 equations. So this is the Lindbladian here, right? But we don't have that structure that you usually see.
So you cannot write that as a Lindbladian master equation?
No, it looks like it's a system of 4 coupled equations, and you need to propagate all 4. Yeah.
Okay, thank you.
Actually, on this slide, I just wonder, do you assume that the network is somehow preserves photon number? Why can you truncate the Hilbert space to this kind of small?
No, we're not truncating the Hilbert space. The Hilbert space is still the same. We just that to get the evolution, we need to propagate 4 different quantities. Okay. Yeah, so you have this quantity rho 1, 1, rho 1, 0, rho 1, 0, and rho 0, 1, rho 0. So they have these initial conditions. Yeah, you need to propagate that 4. But the dimension of the Hilbert space is still the same as the dimension of your original system.
Okay.
Yeah, so each of these operators are density operators on your original system. But you have 4 of them. And the only physical one is this one. So this is the only one that has trace 1, and it's also self-adjoint.
Okay. Just related, like, because the field is somehow, to me, is like non-local. Is you have like a single photon, which is like extend over time.
Yeah. So you have this time dependence, right?
So how can you get like some kind of time local master equation? Sounds very counterintuitive.
So is it a I don't know whether it's a question of semantics, why we're calling it a master equation.
No, I just want, like, you have time local equations where your driving field is highly non-local.
Yeah.
And I just found it very counterintuitive. Maybe, do you have a simple explanation for this?
No.
I knew it was. Madeline, do you want to comment? And then John had a question. So.
No, I have a question.
I didn't hear what you were saying.
Sorry, I have a question. So in the model where you prepare the state by a system before, does it matter whether there is a time delay between the two or not?
No, we're assuming there's no time delay between the two. And
if you would do it with a system far away, what would change?
Well, you'd have to include. I mean, I guess when there's no feedback, it's not really an issue. I guess you could just delay the wave packet by the same by the time delay. But if it was feedback, then it becomes more complicated.
Well, I think it's different because if it's far away, they will be probably independent, while if it's close, they get entangled with each other. Or you assume that there is no. You mentioned something about the systems being uncorrelated. Is there an assumption on the joint state of the two systems?
Yeah, so at the beginning, the source model and the system, they're not correlated. So for example, for this source model, you initialize in this state, right? And then you have a tensor with the initial state of your system. Mm-hmm. So initially, they're in a factorized state.
Okay, so that's all.
Yeah, but the other method, which I started with, this method here is a bit different. So in this one, let's go back to here. So this is a bit different. In this method, you're actually entangling the ancilla with a field. And that's the only source of coupling between the ancilla and the whole system.
Right.
Right, Hendra, I'm not going to ask any questions, so it's just a few comments which may give some intuition to people who aren't familiar so much with this language. Just in case people are wondering whether Matt, yourself, and myself are some sort of magicians coming up with this, or even worse, away with the fairies. There's actually quite a bit of intuition behind this. If you just go back to the thing with the row 1, 1, rows 1, 0, etc.
This one.
Okay. So what we want to do here is to have a single photon input into a system. Okay. So you say, well, we know how to do things when there's a vacuum input. So how can you turn the vacuum into a single photon? So this goes back to a paper by, I think it's Gardner and Perkins, who showed how you can get, say, from a vacuum input field into something non-classical. So for instance, to get a single photon, what you need to do is to have downstream an ancilla, which is a two-level atom, in the excited state. So the vacuum comes into the two-level atom. At some stage, you're going to get emission from the excited state down into the ground state, which will create a photon, which then goes into the output. So the idea is then downstream, this goes into your target system. So what you want to try and do is make it look as if the target system is being driven by a single photon, when in reality it's a vacuum, an ancilla two-level atom, which is then cascaded with your system downline. And then you have to show the mathematical equivalence of this. So when you're looking at this, why is there 4 rows? Row 1, 1, 1, 0, 0, 1, and 0, 0. The best way to think of this is you're looking at states of the system, but it's also tensored with the states for the 2x2 ancilla, which is 4x4. So it's 4x4 overall for the qubit part, the two-level atom, but also with your system. So we get this hierarchy of equations. Row 1, 1 is the one we want. Why the rate of equation? Well, this is actually Zola and company derived this. So this is the unconditioned dynamics. I'd say it's perfectly Markov once you include the ancilla. It's just when you try and trace out the ancilla, then it becomes non-Markov. The thing is, why in the rate equation for row 1, 1, you get all the lower parts is basically because you're describing some interaction which has created or destroyed, moved you down in your two-level atom, okay? But you get this triangular structure, so at each level, it only depends on the lower levels. So you first of all work out row 0, 0, then row 0, 1, and 1, 0, and then finally plug it in back to row 1, 1. So more generally, we can do other non-classical states. And again, the sort of intuition is to try and say, well, what sort of system do you need beforehand, right, that would accept a vacuum and then give you some sort of output corresponding to the non-classical state. So we did it for cat states, several forms of multiphoton states as well. Okay, I hope that helps.
Thanks, John.
Thank you, John. Thanks for the clarificatory comments, a lot of them, I would say. So I I see a question from Asia.
Yes. So I had a question about, I guess, for both of you. So yeah, so I understand this explanation, which is very nice, but it seems like it corresponds to the case where you have this device which is producing the let's say the single photon state, and somehow the flying photons are remain entangled with this device, and then interact with your sequel system, the second system. Mm-hmm. So which makes it really fully relevant that they should be entangled afterwards, and so that's why you need this extended density matrix. However, you could imagine a different situation. You could imagine, for example, a nonlinear crystal where you send a coherent field inside this nonlinear crystal. At the output, you have a unitary evolution which has undergone this coherent state. You have a Schrödinger cat state which comes out and which then interacts with your system. So in this situation, I don't feel that you need to have an ancillary system to model the system, because you see, the flying photons are not entangled to anything. They have evolved, that you have had a unitary evolution on the flying photons. What would you do in that particular situation?
So are you saying that you're creating the cat state inside the cavity and then releasing it?
No, that's exactly what we don't want to do. Basically, you just produce a coherent state, you send it, this thought experiment by Curie and Stoller, where they imagine that you have a very long nonlinear crystal, mm-hmm. and you make some coherent state evolve in this nonlinear crystal, and it produces some Schrödinger cat state mm-hmm. at the output. This should be a unitary evolution of the flying photons, right?
Right.
So, and then you shouldn't need, in principle, you shouldn't need an ancillary system to explain that. You shouldn't need an extension of your density matrix to explain what's going to be the effect of that. So if you want to model, let's say this is going to be the output, the output of this nonlinear crystal is going to be the input of another quantum system. And you want to model the evolution of that other quantum system. How would you model that?
So yeah, the way that we've done that, I mean, we have considered these cat states. And yeah, the way we do it, we still needed a generator for that. Yeah.
Yes.
So maybe what you're saying is true, but we don't know how to do it that way. Yeah, so the way that we approach it, we still have the ancilla that generates that cat state. And the other thing about cat states that's peculiar is that with a single photon state, if you consider just one, a regular coherent state, right? Then you don't. So what we find in that, when we do the cat state, is that you get this dependence on T. Yeah, so there's this additional dependency, and that's because these cat states, they're not orthogonal, right? It's a different cat state. You can't, with a coherent state, you can somehow get rid of the factor of time T, because they become unitary and they disappear, right? But when you have these cat states, a superposition of them, you can't get rid of that because they're not orthogonal. So we somehow retain this RT, but we don't know how to do it without using an ancillary. Of course, you can do it also this other approach, but then also that embeds it into a larger system as well. Yeah, so it might be possible, but yeah, I don't know at the moment.
I think that's the last one because we have the picture.
Okay. Our intuition would probably be that this nonlinear crystal is some sort of ancilla, and probably try and model that way as first. I just maybe also mention okay. So for instance, I have a paper with Guofeng Zhang where we just consider the ancilla to be an ensemble of oscillators, okay, maybe a bunch of cavities. And if the state of the cavity is maybe something like cat state or whatever, multiphoton state, there's a tendency for that to be then almost teleported to the state of the input to the system, as the output into the system. So there's a general tendency for this to happen in these cascaded models. Yeah. Okay.
Thank you. So I think with this, I don't know how strict the constraint is for the picture, but I like to thank the speakers of the afternoon together.